You may not realize it, but all of these things have one thing in common. They all exist because of Fast Fourier Transform.
Every compressed image, every phone call, every MRI scan, they all depend on a single breakthrough from 1965.
In audio analysis, it breaks sounds into frequencies for noise reduction, pitch correction, and music production. In medical imaging, it breaks electromagnetic signals into components that form MRI and CT images. In seismology, it breaks ground vibrations into frequency patterns to identify earthquakes and detect underground nuclear tests. Basically, every time there's a signal that needs to be processed, there's a great chance that FFT is involved.
In 1822, French mathematician Joseph Fourier proposed a revolutionary idea. Any periodic signal, no matter how complex, can be represented as a sum of simple sine and cosine waves. This is the Fourier series. Each coefficient tells us how much of each frequency contributes to the overall signal. This formula became the foundation of signal processing. But what about non-periodic signals? Signals that don't repeat or that stretch to infinity, effectively making them non-periodic? Well, the Fourier transform extended this idea to continuous signals. Instead of just one repeating period, it analyzes the entire signal across all time, expressing it as a continuous spectrum of frequencies. For each frequency, we multiply them together and integrate. That integral acts like a score. If they match, the score is large. If not, the positive and negative parts cancel out.
The Fourier transform essentially acts like a machine that can deconstruct these complex, non-periodic waves in order to identify all of the frequencies present. This eventually turned into discrete Fourier transform, or DFT, where instead of an integral over all time, we use a summation over n samples. The DFT was theoretically perfect, but practically too slow for real-world applications. Now you may ask, why was it so important to make it fast? Oh yeah, war! Mathematicians and engineers scrambled to speed up computations so they could distinguish natural quakes from nuclear tests. In effect, DFT was much too slow for it to be a solid deterrent. That is, until two mathematicians found a shortcut.
Back in 1965, James Cooley of IBM and John Tukey of Princeton discovered something remarkable. The DFT was doing the same calculations over and over again. Recall that DFT formula from earlier? The part we care about is this expression here, often called the DFT kernel. This is a core computation inside the DFT. When we substitute that kernel back into the equation, what we essentially get is this matrix representation. Each entry is just the kernel raised to a particular exponent. In other words, computing the DFT matrix essentially means evaluating this kernel at every kn combination. What Cooley and Tukey noticed was that many of these kernel values actually repeat. The matrix is full of redundant calculations and recurring patterns. And so, what naturally followed was seeing if instead of recomputing the same values every time, we simply reuse them. Their algorithm, what we now know as the Fast Fourier Transform, reduced computational complexity from n squared to n log n. That's a massive improvement. So how exactly did that work? Well, here's the key insight. Divide and conquer. FFT splits the signal into two halves, all the even index samples and all the odd index samples. This decomposition is the heart of FFT. We can express the full transform as a combination of two smaller transforms, one on the even samples, one on the odd samples. But we don't stop there. We recursively split each half again and again until we're left with individual samples. After all, at the bottom, transforms of single elements are trivial. They're just the elements themselves. As we combine results back up to the tree, this is where the twiddle factors come in. To understand the point of these twiddle factors, it's important to understand how we even got to this even and odd split in the first place. Most of the derivation for the Fast Fourier transform is rooted in this mathematical identity. Specifically, its use when helping us split the DFT formula into even and odd components. Let's start by just replacing n in the original formula with 2n and 2n plus 1 to represent even and odd components respectively. For the even component, it's fairly straightforward. We just use the identity we defined earlier. For the odd component, notice how the plus 1 in the exponent just means we're multiplying the summation one more time by e, which, when we factor out, looks like this. Notice how this conveniently leaves us with the formulas for the even and odd components shown earlier, of which are nearly identical barring the change in the index for x. Also notice that once we abstract those two expressions, we are left with this expression right here. This is our twiddle factor, which we can pre-compute and add to our final sum as we go back up the tree. We can sum this up neatly in this formula, where the first and second equations respectively compute each half of the frequency bin range. This gives us the same result as DFT, but allows us to compute for it in a fraction of the time. Now, with that foundational logic out of the way, let's further analyze why FFT is so much faster. Let's look at the structure of the computation. The tree has log n levels because we're halving the problem size at each step. So for 8 samples, that's 3 levels. For 1,024 samples, only 10 levels. At each level, we perform n total operations, combining all the subproblems. That's n operations per level with log n levels total. That's O of n log n time complexity. For audio signals, this is the difference between minutes of processing and real-time analysis. FFT made the impossible actually practical. As for space complexity, FFT can actually be implemented 2 different ways. The both of them have O n log n time complexity, but have differing memory requirements. The recursive approach creates new arrays at each level, with log n levels and n elements per level. That's O n log n space. However, there's a clever trick, bit reversal permutation. By rearranging the input array in a very specific way, we can compute everything in place. This iterative approach uses only O of n space, just the original array, with a few temporary variables on top. And since we've been talking about arrays, FFT speed isn't just mathematical, it's structural. The algorithm is perfectly suited to arrays for a couple of reasons. First is constant time indexing. FFT needs to access even and odd indices directly and repeatedly. Slowing that down would slow the whole algorithm a lot. Thankfully, arrays provide constant time random access, perfect for this. Second is the contiguous memory layout. Array elements sit next to each other in RAM, so the CPU loads them into cache together. This minimizes cache misses and maximizes speed. Third is single instruction, multiple data compatibility. Modern FFT libraries use vectorization to process multiple values in parallel. This only works because arrays have a predictable memory layout. And lastly, we have in-place modification. Arrays allow FFT to reuse the same memory space for intermediate results, which reduces memory overhead. You can try doing all of this with a linked list, but everything would take way longer to do. In contrast, FFT and arrays are the perfect match. And so, from Fourier's 1822 insight about decomposing signals into sine waves, through decades of mathematical development, to a Cold War breakthrough that changed computing forever, the Fast Fourier Transform proved that algorithmic innovation can transform entire fields. It's not just faster signal processing. It's a testament to the power of clever thinking. From impossibility to ubiquity. Now that's fantastic, Fourier. And with that, thanks for watching. You can scan the QR code for a link to our Medium article discussing this topic, in case this video was too fast, but not too Fourier for you. Till next time, see ya!